Okay, well, it seems like there are even more people here than before. I understand you're not only from here, you're also from other areas of India. So thank you for traveling here, and I hope I make your time worthwhile. We're talking about LiDAR. We already did talk about LiDAR. Great introduction. I'll repeat a few concepts, but I'll try to skip a lot of my slides because you stole some of my slides from me. Now what you see here is two representations of LiDAR. You see points colored by what they mean, or what we think what they mean. It's a subjective coloring of points. And what you see here is a surface put through the points, and the surface is lit with an artificial light source to create a hill shading. And the only reason to have that is really to look at the points. It's only for human eyes, because human eyes are used to understand the scene when we have 3D shading of the scene, because that's how our real world is looking. Why do people collect LiDAR? Well, the number one reason people have been collecting large amounts of LiDAR flown from an airplane has been disasters. Because when there is a big disaster, the people are looking at the government do something, and then the government goes to the scientists, and in recent years, maybe for the last 10, 15 years, the scientists have said, well, if you have disasters with water, it's really good to know the topography of the terrain, so we know how the water will flow when it rains, or when the storm surge comes, or when the tsunami comes. You know, water either comes from the ocean, or in forms of a storm surge or tsunami, or it comes out of the sky, often in the mountains, and then it collects, and then because we cut off the trees, the water comes much faster than it used to, and then it causes devastation in the cities. So one project in the Philippines, on a national scale implemented at the universities, I've been very fond of, and I've spent almost a year in the Philippines, because they decided, let's do it for almost the entire country. Now, the Philippines is much smaller than India, but it's still a big country. It's 300,000 square kilometers. And so they wanted to create a 3D model for most of the country that has flooding problems. And more importantly, do it themselves. Not hire some company from Taiwan or from Canada or from Australia to do it, but actually do it themselves within the university system. The idea was, at the end, A, most of the money stays in the Philippines because it's wages and not profits to foreign corporation. And B, at the end, you have all the people that actually really understand the data that will all lose their job at the end of the project, but then they can go to the government agencies and other places to exploit the data. So this is a typical product you want to get from LiDAR. Now imagine that's your terrain. So you want to get something discrete, like a version of the terrain that you can load into the computer. It's a discretization of the terrain, and it's sufficient resolution. And 1 meter resolution is today a high resolution for a big country. Very small countries like Holland or Denmark, they go to half a meter or even 25 centimeter resolution. But they also are almost at zero above ground, so most of the country is surrounded by dikes. So for them it's really important to get the elevation very accurate. The bigger countries, usually a meter is now the state of the art. And then for every meter, look at the floor here. On the floor you have tiles. I think 4 tiles is about 1 square meter, right here on the floor. Now imagine India covered by tiles that are as big as 4 tiles. Now in the middle of every tile, put 1 number, expressing the elevation at that place, plus minus 20 centimeter error is okay. That's something that LiDAR can deliver, this kind of information. And you need, you've already seen it, you need the range finding. I'm not going to talk much about the range finding, but the range finding is one component. It just tells you how far the plane is away from something it hits. But you also need to know where the plane is, GPS. Really precise, GPS ground station. And you need to know which way that plane is flying, and the roll, and the turbulences. So you need the IMU, or inertial units in there. So that's a lot of mathematics and happening to get you eventually the XYZ. But there's a lot of mathematics happening, lots of sensors that need to be collected. Just look at one more example, one more time. Here we have our plane. Now we're just looking at one shot. One of these many shots. And maybe we have 200,000 shots per second. Now we're only looking at one shot. This beam I show you does not exist. It's not like in Starship Enterprise where you say, beam me up, Scotty, and then you go up the laser beam. No. This is just the trajectory of a pulse of light. And the pulse of light is maybe, when it reaches the tree, is maybe this wide. The footprint is about a dinner plate. When the plane flies about 1 kilometer high. And it's about this long. It's like a blob of photons. Most of the photons are in the center, and then they're sort of, you know, it's a bit fluffy. A fluffy blob of photons, this big and this long. It's about 4 nanoseconds long in time. Yeah, so this travels down, and then it hits things. And don't worry about the bird. It's a very soft light. You know, it's like a lav laser. It's not the James Bond laser that would roast the bird and then, you know, fall down like a roasted duck out of the sky. No. So if the bird is small and the laser is this big, then part of the energy, part of the photons will fly back to the plane, and the range to the bird will be recorded in a multi-LiDAR, multi-return system. Now if there's enough energy traveling on, you can have more places where photons get scattered back to the plane. And in this beautiful case, which doesn't happen so often unfortunately, you get 6 returns, including the one on the ground. Now we really like the one on the ground. Most people, especially hydrologists, archaeologists, geomorphologists, volcanologists, almost everybody, also forestry people, they need the one on the ground. They don't really care so much about the ground, but they need the one on the ground to calculate how high this one is above the ground. So the ground one is the most important one. But also the laser is pretty good in penetrating. It does not always reach the ground. Very often it doesn't reach the ground. For example, if here is a very big bundle of very dense leaves, maybe it stops here. And then all these don't exist. And then we only get 2 returns. Or even more, any Game of Thrones fans here? If this is not a bird, but one of Khaleesi's dragons, yeah, then the laser stops right here. We get 1 hit on the back of the dragon, and hopefully we didn't make it too angry. So how many hits you get depends on how many times the beam gets sort of subdivided and can travel on. This is how an airborne system looks like. This is a system in the Philippines.
The energy of the beam will, suppose, go to previous slide. Suppose we are getting 6 returns. So which return will be stronger? First return, the whole your energy is interacting with the object, and at the last, only part of the energy is interacting. So the return will be less from the 6th return.
Yes.
Or it will be same as the first return is getting.
No. Good question. So if, imagine there's no tree and just a parking lot. If the parking lot is black, I get 1 weak return. If the parking lot is white, I get 1 super strong return. If the pigeon is white, I get 1 pretty bright return. If the pigeon is black, I get a very weak return. But no matter what, all these returns, no matter the color and the reflectivity, whenever there's the first return, the next returns have less energy. How much energy they really have depends if this is a white tree full of white flowers, this can be, and this is a black bird, then this can be a stronger return than this one. If the ground here is painted super bright with white, this can still be a strong return. So it really also depends on the reflectivity of the objects. But you're correct, this ground, if it's the same color as this ground, this will have less intensity. Because the energy, the photons were already lost on the way, and actually they're getting lost again, because when the light travels back up, maybe the bird has flown on. No, it has to be a really fast bird. We're talking light speed. But the bird will still be there on the way back up, and it again will block some photons, because it has to travel both ways. Go down and get back up to the plane. Good question, thank you. So this is how the plane looks like. You put the LiDAR here in the hole. This is actually the Minister of Science and Technology of the previous administration, christening the plane, and then they were flying those planes. Here's some early coverage of this Philippines. That was the initial plan, but it was such a good success that afterward they went to almost cover the entire of the Philippines, except I think Palawan, because very few people live there. It's a bit remote. And this is a bit older, but here you see what happens actually in the head office. The planes go fly every day. One of these colored strips, that's one time the plane goes. It's about 40 kilometers long and 5 kilometers wide. Takes maybe 3 hours. The plane flies back and forth and back and forth. And then it comes back, lands, they get the data, and if the weather is still good, the plane starts again in the afternoon and does another 3 hours. And then you only get this much of the country. And this is at the time they had 2 planes in the beginning, so you have 2 colors. Later they hired 2 more planes to be faster. But it is a laborious process. And it maybe sounds exciting at the beginning to be part of a survey team. You know, once you sit multiple days for 3 hours in the plane, let's turn on laser, turn off laser, turn on laser. They don't have in-flight entertainment, there's no good meals served on the plane. It's hot and cramped. So yeah. So I do LAStools. Why do I do LAStools? Well, my postdoc led to that. I was just concerned with how to turn a lot of points, and I use LiDAR points, into a triangulation using a streaming process. And that worked really well. So I wrote another paper, how to then turn the triangulation into a DEM. Because I learned DEMs are very important to people in GIS. So I sent my paper to a GIS conference. And the reviews for my paper were so nice. I was like, wow, people in GIS are so much friendlier in their reviews than people in computer graphics and computational geometry, where I used to send my papers. So I really liked working with people doing GIS. So that was the moment I became the GIS/LiDAR person. Now the first time I got a LiDAR format, it looked like this. ASCII numbers, X, Y, Z, intensity. Okay, it's easy to work with. You know, everybody understands ASCII. I can easily write some code to parse it, and it was helpful in the beginning. And it's okay for 10,000 points or 100,000 points, maybe even 1 million points. But now we're talking about billions of LiDAR points, and then ASCII is not so useful anymore, because ASCII is made for human eyes. We can read that number. The computer can read that number too, but it doesn't know what it means. It has to translate it first. Hence, it's not a good idea to store it like that. But there was a bunch of people from industry. They created the LAS format, and it was then donated to the American Society of Photogrammetry and Remote Sensing, because it was so. Okay. Sounds like it's coming on. Oh, that's good. And this LAS format has become very, very successful because it's very simple. And many software companies started using it. That's how it looks like. The file has just a simple header, and in the header it says things like, which version of the format are you? Which date were you created? How many points are in the file? What's the bounding box of all the points? Very simple things. And after the header, for every return comes one of these structs. The most common one is this one here. X, Y, Z, intensity, and the return number. That's actually missing in most ASCII things. The return number and the number of returns, meaning return number, these two fields here. Return number and number of returns. By the way, you have this presentation on your USB drives as well. The return number tells me I'm return number 1, and the number of returns tells me I'm return number 1 of 6. So that would be that duck that was hit. That was return number 1 of 6. And the ground hit would be number 6 of 6. And the 4 vegetation hits would be 2 of 6, 3 of 6, 4 of 6, 5 of 6. This is very complete information. How do you know the points belong together? Because for each of these 6 returns will be one record like this. How do you know they belong together? They're from the same shot. Well, that's because you store the GPS time of the shot with each of these points. So, in this case, there should be 6 points, all having the same GPS time, but having different return numbers. But they all should have, I'm from a shot with 6 returns, so the 6 should be the same one. But then there are slightly different X, Y, Z coordinates, and slightly different intensities, depending on how bright the reflection was. That's really it. And if you have a file with 67,455 returns, you have the header, and then you have 67 star million, whatever number I said, times this one repeated in the file. That's very simple. And because it was so simple, it was very successful. However, when I got my first LAS file, I'm like, oh, what's this? It's just a binary file. I can't read it. ASCII, the advantage is you get it and you can open it in a text editor and you can read it. That's one advantage. But if you have 1 gigabyte, then you have trouble with the text editor unless you use a clever text editor. So I got LAS files and I needed to read and write them into my own software so I could triangulate my experiments. I Googled, and I couldn't find anything. But I'm a computer scientist. So I downloaded the specification and wrote a little API, application programming interface, to read and write these files. That's really easy for somebody who studies computer science. Like read next field, read next field, read next field, write next field. That's actually kind of fun. It's almost an exercise. And then on top of this, I wrote a few small, simple tools to help me with my own research. I wanted to view the points, I wanted to look the info, I wanted to see what's in the header and how many points are there and what are their values. Give me some text to the description that I can understand. And then some, because I had a lot of text. And I remember how fast it was to read binary. I wrote text to LAS, so I converted all my text formats into LAS format. And also wrote a compression, because that's something I did for my PhD, compressing geometry. And when I was done, I thought, oh, that's kind of useful. I put it on my webpage, and the rest is kind of history. I didn't realize that one day I would be doing this professionally. Because, so if you ever have a really cool little software project, or some other thing, and you think, oh, I want to share this with others, I put it as open source on my webpage. Think about the name, because I just used the folder I had it in, which was called LAStools. Makes sense, right? I'm working on LAS, I made tools with LAStools, and I zipped it up and I put it on the floor. So everybody called it LAStools. I go to a conference, and the woman looks at my badge and say, Whom are you working for? LAStools? Wow, that is a crappy name. Everybody will think, I'm working on wooden bar furniture in Southern California. Right? Stools. Bar furniture. Right. Crappy name. Okay. So, I turned it into a company eventually, and I added the GUI before it was all command line, and a toolbox for ArcGIS and QGIS and Earth as Imagined. But most importantly, I started to, because I got a whole bunch of emails before, I started to be a bit more organized with the emails. I thought, no, don't ask me personally. I make a group and you can ask there, so I don't have to answer everybody's email all the time, again and again, the same question. And that was a very big success, because now this user group on Google Groups is a bit of a treasure trove for all kind of LiDAR questions. You can search it and find a lot of things. And also on Facebook, if you go to the LAStools Facebook page, for example, you'll see the group I was with in Pondicherry just last week. It's a bit of a more social side of LAStools, not so serious. Okay, you all have a USB stick, right? Or not really a stick, a USB flash. Yeah. So what I would like you to do now is plug that into your computer and uncompress the one file that's on there, so we can start our first introductory exercises. So this USB stick will have one single file on it, I hope. That was the idea. One single file called something very obvious, with workshop and where we are and the date.
Excuse me, ma'am. There is some issue here.
They should expect it.
Okay, don't extract it.
Well, I mean that's. So you should have this one file here. Only one file. And the whole installation process is you go into that file using the Explorer, and then you will see one folder called LAStools. And now you copy that onto your hard drive somewhere. For example, on the C drive. Yeah, so if I take this folder now, I drag and drop it. I drag and drop it onto the C drive. Now I'm not going to do this because I already did it. So yeah, I would now just let go the mouse button and it would start extracting. That's gives you error. Not able to unzip. Well then something went wrong in the copying. I washed my hands in innocence, how we say in Germany, because I didn't do the copy, but I have the originals here. So anybody who has problems, does it work for you? Okay, yeah, let's just go, does yours work? Does yours work?
Copy it and copy.
Okay, had I known this, I would have done that at the beginning of my lecture, or actually at the beginning of your lecture. We'll try. So don't extract it from the USB drive, just copy it onto the desktop. and then extract it from the desktop. It seems some are working. So please, if your credit card size USB sticks work, don't block the other ones. Because
Who is having problem? Everybody is having problem.
You just plug in.
Okay, index is there. इसमें सारे बात नहीं है, सारे नहीं है, कंप्लीट फोल्डर नहीं है, इंडेक्स से पूछ के कंप्लीट
yeah, that's weird. I need to format that right. Something is funny with that right. Okay, let's see. I can try to make it a good thing.
Here everybody has extracted. Extracted or not?
Yeah, that's something weird. The moment I put it in already. If you have a copy that works, if you could just format the disk, which doesn't work, you know, if you have a disk, your neighbor has a disk, it doesn't work, if you have a copy that does work, just format this thing, and then copy the good version on it. Then we can speed up the process of, like I'm doing it now, but I only have 2 slots.
It's almost down.
Folder, and you drag and drop it somewhere convenient. Ideally, somewhere directly on the drive, so your path is short. So I copied mine to the C drive, but maybe you want to copy yours to the E drive or the drive called C/software, but not something super long, not like C/my document /my program /my source from LiDAR software /LAStools workshop /LAStools, because then every time we're running the software, you will see that very, very long path. And in the this evening you can move it somewhere else. Okay, once you did the copying, you have exactly this folder that you see here. And all the programs are in the bin folder. Inside that folder is where the LAStools software is. All the other folders are other stuff. In particular, this is the open source compressor. There is C++ open source software in there for the compression and uncompression of LAS to LAZ files. LASzip is also open source. It's the engine behind LAStools that does all the file management, all the filters, all the transforms, lots of utility programs. That's also open source. In the source folder, there's C++ programs, I think 6, 7, or 8, or 9, or 10. They are also open source. They are part of the LAStools. They show you how to use the library to write new tools, for example. But LAStools is not only open source, and if you look, there's a file called license, and it says there's 2 parts of LAStools. One is open source, and all those sources you get, and basically when you have a source, then the tool is open source, and some part is closed source. And the closed source part is how I mainly finance myself by selling licenses to the closed source. I sell academic licenses and I sell commercial licenses or government licenses. But the other tools also work without a license. And that's the special. So these are completely open. These are completely open source, all these tools. Anybody can use them, commercial, non-commercial, doesn't matter. Now, then there's some freeware. You can use them, also commercially, but I don't give you the source, just because there's some of my secret sauce in there. But it's basically also, this is freeware. And these ones, these are the tools, they also all work, but they will add slightly bit of noise to the output when you use them without a license. I have designed the noise in a way such that most researchers, hobbyists, educational people can still use it without being too much affected, but so that people that use it for production or for profit have an incentive to purchase a license. Because somehow, I'm a one-man company, I need to get funds. And yeah, so they still will work, but they will work a little less good unless you chop up your data into very small tiles, maybe 200 by 200 meter tiles. Then they also work without any distortion. So I mean, if you're clever, you can use LAStools without a license. And if you're not clever, then either buy a license, or if you just don't, if you make a lot of money, because LiDAR companies charge a lot for that service, processing companies, then you can possibly afford a license. So it's kind of a bit of a tightrope walk to enable everybody, but also make sure I can continue to do what I do. Okay, I would like now to basically do the first exercise using this rapidly user interface. That was the last slide where I stopped. And by basically running the simplest of all LAStools, and I told you where to find the LAStools in the bin folder. So you go into the bin folder, and then you go down and down and down. Well, first let's sort it by name. Sort it by name. And now you see all these LAStools. Now, very important. The icon needs to look like this. If your icon looks like a box, that means you didn't decompress the folder yet. So the icons should look like these little logos here. Windows allows you to look at a compressed folder, and it looks almost the same as an uncompressed folder, which I don't like very much because it confuses people. It will only work, what we do now, if you see these kind of icons. So and then simply search, but don't search in the search box. That's another thing. Windows makes some funny things if you search in the search box. Search by looking through all the names through a tool called lasview. Lasview. View like having a look. So basically, get to this point where lasview is slightly blue, and then double click it. And then my beautiful, beautiful GUI should open. And when it will now say it's licensed, because you do have now a 30-day license on your academic license on your laptop. So, what a beautiful GUI. So this GUI is a little different than the Windows GUI usually look like. But I didn't used to have any GUI, and then people said, oh, please, we want a GUI, and then I made them a GUI. I said, oh, but we want a nicer GUI. No, that's the GUI you get. So what do I see here? On the left-hand side, every tool has a GUI like that. On the left-hand side, they're all the same. On the right-hand side is specialized for every tool. The bottom is also always the same. You can think of the GUI being a bit like a control station for the LAStools. Now the viewer is the least interesting processing of LiDAR because it's just viewing. It's not even a good viewer. But for teaching purposes, I find it a sufficient viewer. There are many free viewers out there. You can just Google for free LiDAR viewer and there's at least 20 different ones. Now I want to load some data into the viewer. When you click the browse rollout, then you see the directory actually shows up. And you can maneuver through a double click of that /dot, you go up one directory. If you double click here, click, you go up one directory. And now you see the directory that you've seen before. That's the main LAStools directory. Yeah, if you go up one more, then you see whatever you have in your drive. All the stuff on the drive, LAStools. I go back. And there is a data directory. Data. And I want you to go into that data directory. So again, when you started, you were in this directory. And you already see the data we've been using today. But you go up one directory. I right now just want to familiarize you with the use of the GUI into this data directory. And then you see a whole bunch of LAZ files. LAZ is compressed LAS. SZ. The only difference is it's much smaller. It contains exactly the same content. The compression is lossless. And then I would like you to load one of those files. This one here, fusa.laz. How do you load it? You just double click. Click. And now, oops, what happened? We got a blue box. If you now close this again, this rollout, close it, then you can see a little bit what's in the file. Because right here, I'm reporting the last header. And I talked about this a little earlier. This is the header of the last file. It tells you which version it is. It tells you the day it was created, the 40th day of 2010. It tells you the number of points, the point type. Remember I said point type 1 is the most common one. Point type 1. It's 28 bytes.
How do you get this file? How do you get this metadata file?
So that is, as soon as you load, maybe I do it one more time. So I start with the viewer.
Yes, that has been done.
I'll go to browse.
Okay.
I go up one directory. I go into the data directory by double clicking. I see the FUSA and I double click. And now I just close the browse button again, the rollout. And then I can see the header information. And I also see the projection. I'm in UTM zone 54 south. So that's in the southern hemisphere. And if you know your UTM zones, then you know that should be in Australia. Also. That is actually in Australia. FUSA does mean not what we think. It means Flinders University of South Australia. And yeah, but this is a viewer, right? We don't see any LiDAR points yet. In order to actually view, you have to press this view button here. Press it once, and another box comes up. And here you see the actual command line that is executed in order to start the viewer. I didn't immediately start it. I want to first show you the command line. And that's one of the nice things about my GUIs. My GUIs teach you the command line. Now that's a very simple one. It's like, oh, why do I need to learn that? Well, if you become a professional user of LiDAR processing in general, you will want to do batch processing and writing scripts. And for that, it's useful to know the command line. You can even edit the command line, which we will do in a later exercise. Or you can copy it, but right now I want to just start it. Start. And now the actual viewer is starting, and you should see the point count. That's what we have now, after starting the viewer. I will repeat the exercise with a different data set in a little while, because I know not everybody managed to follow this time. But don't despair, next time you can follow. So initially, you are in a pan mode, meaning when you move the mouse and you hold down the mouse button, the scene is panning. What you see is LiDAR points colored by classification. You can change the coloring by pressing C on the keyboard, C like color. And then it goes for different coloring options. All the different coloring options that are there. Right? If you want to change the interaction mode, you press space. Then you go from pan, which is this mode, to translate, which translates the data up and down, or to zoom, which allows you to zoom in and zoom out, zoom in, and tilt, which allows you to shake everybody out of their beds. And one more gets you back to pan. By holding down Shift, Control, and Alt, you can directly go to these modes. If I hold down Shift, I go to Translate. If I go to Control, I'm directly in Zoom mode. And if I hold down Alt, I'm in pan mode. This is just because it makes it easier to navigate. There's also a menu which allows you to look up everything. If you right click, the menu opens up. And for example, changing the coloring mode, you see in the menu, the C is in brackets because the C is a hotkey. Meaning you can type the hotkeys on the keyboard and not use the menu because the menu is slow, and after a while playing with lasview, you get used to the keys. Also the coloring, you can directly go to color by intensity. Now it's difficult to see because I zoomed in so much. I want to make the points bigger. I can press equal on the keyboard. Equal, equal, equal. Oh, now that looks much better. How do I know it was equal? Well, if I right click and there is again a menu option which I could use, but it's very slow because I have to open the menu every time. There's a little equal sign in brackets. And it also tells you how to make the points smaller again by pressing minus. If all your points disappear, maybe you press minus too many times. Then they become size 0. Oh, and now it's 12 o'clock. And we do a small break. We're a little behind now because of the USB stick crisis. But we'll make up for this by staying until 8 p.m. today. Right?
This point
All right.
equal, but it is doing this point equal. It is
Makes the points bigger just for rendering. It just shows you bigger points.
which make visualization more appealing.
Well, if you zoom in, the points become very sparse. Look, when I zoom in, I press Shift. I press Control. I zoom in. Eventually, the points are very far away. I can now make them very big, to get the scene filled again. But of course, now if I zoom out, they are way too big. I want to make them small again until they kind of fill maybe like this, so I still know their points. It's just an aid for visualization. This is not really LiDAR processing yet. Right now we're just doing a little bit of exploration and learning the menus so we can later do the real LiDAR processing and also learning what it means. But now it's time for a tea break.
Is there any logic?
Huh? Okay, we should be back in 10 minutes. Well, in 5 minutes because then you will not come back. After that.
He needs an access to the laptop.
Okay. I'm just going to close everything that's open right now and start right so that I don't know when you lost your windows or something.
You can tell Srirag also. You can tell Srirag to do it.
By pressing escape, you can close the program. And I go back to the last view and I start it again. I just repeat one more time the same thing. I start last view. I go to browse. Browse rollout. I'll go up one directory by double clicking the second menu item, which is /. I go into the data directory and I load FUSA. And then I close the browse, rollout, and again I get the same information I've seen before. And in order to actually run the viewer, I need to press view. I see the command line, and then I press start. And then I get the default view of the classified LiDAR point cloud. How is it classified? Well, you can actually, if you go with your mouse pointer on top of one of those points, maybe make them a little bigger by pressing equal. And now you press I like information. You can probe the point and it will tell you here the coordinates of the point I was above, whichever point you are above. You just go above a point, you press I, and you see these are building points. They are classified as building, class 6. That's a classification code that we all agreed upon that will be a building, class 6. You see the intensity, and you see that it's the first and the last return. That actually means it's a single return. If I go over the green area and I press I, it tells me it's vegetation return, class 5, IIST. I also see the coordinates of this point, and the intensity is 24. Maybe I'll try this one here. Intensity is 35, also higher vegetation. And if you go above one of those round points, and then it says ground. Ground is an intensity of 108. I believe that's where road, maybe here. That's a road. That's probably a black tar road, and here the intensity is only 44. Roads usually don't have very good intensities. Well, you can visualize the intensity by color by intensity. And then you see that the road doesn't have a good reflection. I put it equal one more time. So now I almost have a photograph, like a panchromatic photograph. You see the open field reflects pretty well, but here the individual leaves also very dark. And the roofs totally depends. Some roofs have good reflective material, like this roof here, or this roof here, or this roof here. But there are some other roofs, this one and this one, which are very dark. So then it depends on what material it is made out of, and also if the roof is wet or not. Like if you fly after rain, the wetness. Wet tar is the worst for LiDAR. Wet black tar. So here you see all the buildings classified, and now I look at the intensity, and you see they're very different. The intensity of these roofs. So what else can you do? This data is already classified. So you can look at different classes. For example, if you press B, B like building, then you only see the buildings. If you press V, V like vegetation, you only see the vegetation points. And if you press A, you see all the points. And you can always change color by pressing C. Now let's look at the first thing the laser hits. The very first thing is the first return. You can get the first return by pressing F. F like first. And then you get, in this coloring, color by return. If I look at the first returns, I get yellow and red points. What's the difference? They are all first returns. But the yellow points are the only return. They are single returns. Now a single return is also a first return, but it's also the last return because there's only one. It's the first and the last. Whereas the red ones is more than one return. It's the first return, and then there is also some other return later. But I only show the first returns right now. You can make a surface from this, a surface, by pressing T, like triangulate. And now you don't see the surface so well, the triangles, but if you press minus many times, minus, 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 then the points become size 0, and you can only see the interpolated surface, which is actually a triangulation. And you can change the shading, which is just a boring shading here, by pressing H. Why H? Well, I use S for something else. And if you forget all the hotkeys, you can always look up the hotkeys by pressing right-click, shading mode. Shading mode. And now you can remember it. And then you get a different shading that shows you the elevation as well. If I press H one more time, I get a different shading mode. I like this one. This looks nice for this data set. So now we do some magic. I'm zooming in a little bit. This data set was already classified, meaning I already processed it. What we do this afternoon, I already did it. That means I can now press G. G means activate only the ground points. And now I press T one more time, triangulate again. And ta-da! I get the DTM, the ground model. All the man-made structures and all the vegetation is gone. And I can look now under the trees in this area, for example. I can go back, FT, first returns, activated, triangulate. You see all these trees here? GT. Now I can look under the trees and I see, I don't know what I'm seeing. I see some lines. I'm now not sure if those are scanning artifacts or if those are actually lines that are part of the terrain. I'm not sure about this area. But very often when you have fields, you do see the lines like agricultural fields. Even after the crop has grown, if you scan it, you can still see the patterns of the earth under the ground. If you have sufficient high resolution. This is a fairly high resolution scan here. The triangles look nasty where you have big open areas where you don't have any information. If you press H one more time, you see the triangulation. Now wherever I have a building, and that's actually the police station here, it's a big building, I don't get any information on the ground, because in order to get the information on the ground, I need to use a James Bond laser that melts lasers through the roof to hit the ground, and the police would be happy. And so because the roof stops the laser, we must now interpolate across the entire building, and that means we don't have any real information there. Whereas in the open areas, like here next to the trees, if I press H, you see, it looks very nice. Same on the road. Whereas it looks a little more edgy, triangulated here. Whereas here it looks more natural. That's just because I have real information on the ground here. Important, because it's often taught wrong or even written wrong in textbooks, the last return is not the ground return. We look now at the ground returns. Now and now we compare it to the last returns. You can just press L. L, T. That's the last return. But the last return is very similar to the first return, because on all hard surfaces, it's the same return. On all roofs, the last return and the first return is on the roof. Hence, it's not on the ground, it's on the roof. On every car, the last return is on the car. Like actually, what you see here, next to the building, is a parking lot with cars and some trees. If I color by classification, and I make the points a little bigger again, you see that the trees are classified, but the cars are actually, if you press I on top of one of those gray points, they are unclassified. Because I don't have a classification software for classifying cars. Cars are difficult, right? Especially the really low cars. Cars, I mean, I know it's a car because I know it's a parking lot. Otherwise, it could just be really big shoes, you know, I mean, or piles of dirt. I know it's a parking lot because I am human and I know outside of a building, I often have cars parked. And this just looks like that. And if I press G and I triangulate again, then the cars are gone and now I see the footprints. And if I press H to get the triangulation, I can see that wherever there's a car parked, I have no ground points. And I also see that this person here doesn't know how to park. You see, it's not a very good parking job. Okay, so I showed you a little bit of what's in what you can do with a viewer, and I tried to give you an intuition about LiDAR and what the difference between ground and last return. Oh, I remember one more thing I want to show you. I press now Shift T, then the triangulation disappears. You can always look up those things by here. Here there's triangulate and then untriangulate. It's a big T, Shift T. And I show all returns again, A, all returns. Also this you can see, render only, all returns, A. And now render only, multiple returns. Now there's no hotkey. If you right click, render only, and then multiple. Now I'm only rendering multiple returns, meaning returns where one laser shot produced more than one return. And you very nicely see where does a laser produce more than one return. Not on the open road. because it produces only one return. Unless, of course, there could be a plastic bag flying in the wind. Then it can make two. First the plastic bag and then the road. Or a bird. Or a wire to cross the road. Actually, we have some wires here. If you go on the Y, I do understand that I have multiple returns in the vegetation because the laser beam hits some leaves, photons, and then travels onto the ground or to some lower tree. But why do I have multiple returns here? I can almost, if I move it, I can almost see the building outlines. Why do I have a multiple return along the edge of a building? I mean, a building is hard surface. Glass is one thing that can cause that, but that's not what causes it here, because I don't have glass along the edges of the building. No, it's just the dividing? Dividing. Yeah, dividing of the beam. The beam is as big as the clock on the wall. Yeah? So if half the beam hits the edge, then half the photons travel back to the plane. When it hits the side of the roof, I think it's called the eave of the roof. And the other half is traveling on. And you see that very clearly in this building here. I'm zooming on the building now. I'm showing all returns again. And you see it here, for example. Now I press T like triangulate. Here you see it very well. On the main roof, the LiDAR beam hit in full on the roof. But along this edge here, the LiDAR beam was split. And for half of it was reflected here, and for the other half, there's a corresponding blue point on the ground. Here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Exactly. But remember, the way they're connected is computed differently. Now I can also compute where the plane was. The plane was somewhere there. Because I can draw a line. It's a beam of light that's instant. So if I draw a line through all these points, up, there will be one place where all lines meet. And that's where the optical origin of the scanning system was. And the scanning system is inside the plane. So that's where the plane was. You can basically compute the position of the plane by where these beams converge. You can only do that for multi-returns, because only then you have 2 points that if you draw a line up, they will eventually hit where the plane used to be. So, yeah, and you see that also nicely along this entire edge here of the building. You see these returns. Okay. I want to do one more exercise with LASview, mainly because of the menus and because I want to, before we start the real processing. So I just quit LASview, and you really want to do this exercise. So we start LASview again. And you know how difficult it is sometimes to get data from the government. Like data you really want, data you're really so curious about, you could do great things when you have that data. It's really difficult to get data from the government. So I'm a bit of a rogue scientist, you know. I mean, it's not, you know, I got fired from my job for a reason. But now, you know, So let's browse to some government data. So if you go up one directory, you come to this data directory. And if you haven't noticed, in the data directory, there is a subfolder if you go up and down here. Yeah. That is called tremendously classified. Yeah? Wow, what could that be? Hugely leaked LiDAR. Oh my God. What's in here? Obama's fault. So sad. What? Bigly top secret. And then Pentagon.LAZ? Nah, that couldn't be. That's a joke from Art. What's that? What's in here? Okay, it's the file. Okay, it's got 8 million points. Okay. Let's look at it. View. You see, that's what happens when you have a very long file name. It's then very long. And that's for the regular exercises. When I'm not doing a joke, then it's not that this is a joke. So I press start. And then I have this fake, this completely fake fabricated story that Mark is telling here of this LiDAR point cloud here. But if I press C, like change the color, oh, that does look familiar, doesn't it? What could that be? If I press C again, C again, C again, I see different visualizations. Well, that really looks like a very big office building, maybe the biggest office building in the world. Where could that be located? By the way, if you press X, that's a new thing I want to show you. If you press X, you can draw a box. And if you then press X again, this box is zoomed in. And now, ladies and gentlemen, we're actually looking at the real Pentagon. And we can make measurements inside the Pentagon. And we can figure out what this thing is located on top of the building. Maybe some kind of missile intercept or so. I don't know. But you can see the structure in the Pentagon. You can triangulate it pressing T. And just looking at the and if you press X again, I can go in the middle of the Pentagon and I see there's a small Pentagon. And I press X again. So with X, you can go back and forth between the two. And now, what do I see here? Oh yeah, Martin was right. It is classified data, look. It's classified into ground points, which are brown, G, and, oh, there's Pentagon there, ground points, and A, all points, or U, unclassified points. So it's classified into ground and non-ground. Not classified as well as the other points. I can look at the last returns with L, triangulate them, and now I see the little Pentagon here. And if I now make a measurement, for example, from pressing, like you can do very simple measurements with LAStools, like pressing I above one point, and then going to the other end and pressing I again, but holding shift, then it measures this distance. And it prints it, I got it here tonight, it prints it up here. And now you know that the distance I just measured, which is the side length of the small pentagon, is 15 meters. Now we all know that very classified information that the cafeteria of the pentagon is 50 meters in side length. Now what are we going to do with this information? So this is a bit of a joke, because in many Asian countries, also in my country, but we're getting better right now, government is paranoid about sharing information. In the United States, the Office of Technology of Washington, D.C. put in open data the Pentagon. And usually the United States is pretty paranoid about security. So if even they put if there would have been 5 buildings, to not put online, maybe the top 3 would have been the White House, the Capitol, and the Pentagon. But they put the Pentagon online. So I think anytime somebody says, I can't give you the data for security reason of some forest in the middle of nowhere, show them the Pentagon. Say, come on, I got the Pentagon, and you care about your little forest somewhere in the middle of nowhere? This is just sort of a little bit to, I'm a big open data person, and I know it's a big issue in India, and this just gives you a bit of an argument. And now you're all part of my big conspiracy, and you're all guilty, so I won't be in jail alone. So, all right. But no, I have a blog article about this. I'm not online right now, but maybe later I'll show you. I just wanted to make a blog article about the new LAS 1.4 format, and I was looking for data, and I found the Pentagon, and I thought, rather than making it a boring blog about just some other format, I make it a pseudo-conspiracy blog. Where everybody thinks, Martin hacked the Pentagon this time, he's taking it too far. And many, many more people read the boring blog about the last 1.4 format updates than had I just used some farmhouse in the middle of nowhere. Okay. So this was only looking at data, just to give you an idea, to feel how the data looks like. What I want to do next is to actually start processing data. And if I get data, the first thing I do a quality check. And a quality check helps me to know, is the data what I expect? What accuracy can I expect from the data? Because if I'm, for example, getting LiDAR data that has an error of 50 centimeters, and I want to do an agricultural study with baby rice or peanut plants, then it's probably not possible, because the rice, the plants are so small, and the error is 50 centimeters. Now all my calculation will be in the error. But if I want to study coconut plantations, 50 centimeters of error may be okay. So you want to know the error before you start your analysis, and see if the data supports what you want to use it for. So which data? Well, obviously we're not going to use any data from India today. We could use the Pentagon, but we already did that. I try to always collect some data that I'm allowed to use. The closest I found to you that I'm allowed to share with you is from Thailand. But first, I would like to do a small example from Poland. Just because it's a very short example, so it's the shortest possible LiDAR pipeline. So this folder usually doesn't have these subfolders. These subfolders are why the file is so big, 800 megabytes. That's all the data. I put it right here, so it's close to our software. Usually LAStools is only 38 megabyte in total. The other 800 something megabyte is all data. So, first thing, when we get new data, we look at it, just to make sure it makes sense. So one more time, lasview. But this time, we don't have to browse so far. because I put Poland right here. That's why I put them here. So when you open the browse box, you can just double click into the Poland folder and again double click and load that tile. And you already know that if you close the browse box, you can then have a look how many points are in the file. 3.5 million. Okay? And again, it's point type 1. And if I view the file, I get a small tile somewhere in Poland. And this is unclassified data. All I see now is elevation coloring. If I ask the GUI to color it by classification, color by classification, it's all black because all the points are, if I use I, unclassified. So this is unclassified data. I don't know what the points mean. They're all just scan points, like they come from the scanner. One thing I do have, I believe, you have a look, color by flightline. Yeah. I do have flightline information. What does that mean? Well, I have a tile here. Often when you do a LiDAR survey, the plane flies back and forth to cover the area. So points in one tile are likely from different flight lines. And the point source ID that every point has encodes from which flight the point is. And here I visualize it just by giving points from different flight lines different colors. And now you can press in the keyboard 0, 1, 2, 3, 4. Now you see the different flight lines. And you can kind of see, the flight movement. You know, this flight was flying this way, and you see the edge of the flight line. Because the plane is shaking like this as it goes through the turbulences. It is very useful to have this information. This flight line pretty much completely covers that tile. And here you see another partial coverage from another flight line. This allows you to later compute, and we will do that, how well the flight lines match together. And I'll come back to that later. Because if you fly one direction, and later you fly the other direction, and all these sensors, GPS, ground station, IMU, ranging, and then all the software that's used, how do you know that the flight in one direction gives you this points, and the flight in the other direction is this point, and they actually fit together? They could be shifted horizontally, they could be shifted vertically, they could be rotated. There are a lot of sources of error. And in order to make a quality check, we need to know which point is from which flight line to check them against each other. But that's not what we're doing right now. Now I just wanted to show you what's in here. Let's press, here you have the intensity coloring. Again, you see some kind of scene in the forest. If you press X once and X twice, you get this kind of cuts through the forest. And now you can walk by using the arrow keys. And you see we basically have a forest scene. Now we're walking through that tile, just with the arrow keys. So all I did is press X once and X twice, and then I got the default is just a profile across. And it's not classified. But clearly I have a forest. If I zoom in a little bit, you see I have big trees, and then I have smaller trees below the big trees. But I do not have ground information yet. But I would like to know now what's on the ground. And now we will make the shortest possible LiDAR pipeline that we hopefully complete before lunch. Compute the ground, and then make a ground raster, a DTM, a digital terrain model, as a raster of a certain resolution. Okay, enough viewing. Now we do some real processing. we need a new tool for that. And the tool is called, it's a very popular last tool, it's called last ground. There are two versions of it, but for this data set, we can use just the good old last ground. And just double click it, and you're like, oh, again, the same boring menu, same boring GUI. Yes, but it should say something different at the top. And that has many more options on the right side. But we do the same thing now that I trained many times before, and that was one of the reasons we did train. We browse to Poland, click, click. We load the data, click, click. Okay, now it's loaded. You remember, so last ground, and I'll tell you in a second how last ground works. And most of the LiDAR algorithms work like that. You can click what kind of terrain you have. And I didn't see any houses, so I think we could either pick nature or wilderness. And there's usually some experimentation involved, which are the best settings. And I'll click wilderness now. And I'll do extra fine, pre-processing work, or fine. This should be fine. And the output will be in LAZ format. So again, I will create a new file now where the ground is classified. But I need to give it some name. Now, I'm really lazy. There's a very easy way of giving something a name. It's called appendix. So I'm taking the original file name and I'm just adding an appendix. And I usually use appendix that tells me which operations I did. So in this case, I go into this output, rollout, and I add only appendix G. This will mean in the same folder, the file will be written where it's currently in with the new name, that's the old name plus the appendix. Nice and lazy. And sometimes, for example, when I now also did this one, when I open this one up, sometimes you don't see a run button anymore. There should always be a run button somewhere. And that's because opening these menus pushes down the menu, and then you don't see the run button anymore. So if you can't find the run button, it's because you open too many menus, these rollout menus. And now I'm pressing run. And now for the first time you will understand why I always show you the command line. Because now this box pops up. And it looks a little familiar. We already know the beginning part, except it's a different tool. But now we have the options showing up. So we chose option wilderness, option fine, and the output appendix minus OD output appendix is underscore G. And then the output format is LAZ, the compressed format. So every time you use the GUI, you will have to look at that. And after a while, you learn the commands. And maybe one day you forget to put the appendix, or you want to change it to something else, and you can just edit here without going back to the menu. And then one day, maybe you don't even use the GUI anymore. You directly write that into a text file that you use again and again. That's how I process my LiDAR. Start. So when you press start, last ground is running. So what does last ground do? It takes all the points, and because wilderness means a certain thing, it means use a grid with size 3. It puts a grid of 3 meter size over all the points. And it drops all the points in this grid. And every point, in every grid cell, it keeps the lowest point. And says, you are a ground point. And then it moves the grid a little bit, because in fine means it moves it more often. Default, it moves it less often. Ultra fine, it moves it very often in small steps. Now it moves the grid, and again ask, which is the lowest point? Now, if you move the grid slightly, you have different groups of points falling into every cell, so the lowest point is slightly different. Not always, but sometimes. And then you move the grid again, you move the grid again, you move the grid again, and 3 by 3 meter grid. And in the end, I have for every grid, I have a bunch of points. Often it's the same one, but there are also different ones. Then I use all these points together, and I say, you are my initial estimate for the ground. All you points that are the lowest point in one of those shifted grids. And now I start slowly by slowly adding points to this initial triangulation of low points. And that's how the ground finding algorithm works. And that's how it also works in other people's software. It's called thin densification. We try to come up with what's most likely definitely ground, the lowest points, on some grid. Of course, if I have a big house in there, then the 3 by 3 meter grid will still be on top of the house, because the house is bigger than 3 meters. Well, that's why we have wilderness. Wilderness is 3 meters. But there's also city. City is a 25 meter grid. That's for city areas. Like you have IKEAs, you may have to do something even bigger, 50 meters. You want to know more? Well, this is an intro course. But every file has a README. So if you click README, it's called README right now. But in the next version, I will call it Do Not Read Me, because you're more likely to read it then. And then you can basically read all the little details about this kind of the default step size. This is the step I just talked about, 5 meters. And it doesn't even talk about wilderness here, but there's town, then it's 10 meters, and cities, 25 meters. And for IKEAs, there's minus metro. This is the shorthand. You can also directly write minus step and say what step size you want to use. Yeah. One thing, very important, you learn that very quick. There's a close button here. Right now I want to close my tool anyway, so it's okay. But usually if you use a README, and then you go to your usual, this one, not only the README closes, but everything closes. Which is okay, because I'm done with last round. My computation has finished. So now I'm going, I have to quickly have a look. Poland folder. Poland folder. A new file. _G. And when was it created? Oh, at 9:29 a.m. Germany time. Germany time. Exactly. So here it is. Yeah, see, 3 minutes ago. That's Germany time. It's time to practice. Okay, now we want to have a look what's in here. But instead of again opening LASview, we already directly use the next tool we want to use. And the next tool is called LAStools, because now we turn LiDAR into a DEM. But why do I? Okay, now just load this new data set. That should be, you should have that down now. Browse, hold it, and if everything went well, there should be that second data set now. And that's the one you want to load. And it should say, it was produced by last round version that I compiled yesterday in Chennai Airport. That's the date, 17/10/11. And every tool actually has a viewer built in. So you don't need to use LASview, you can always just start a viewer from every tool. So I first want to have a look. What did I produce? Did I create a ground? Well, that looks very promising. I see lots of brown points. If I press I on top of the brown points, it says, yes, flatland is ground. If I press G, I get ground. Press A, get all the points. And then, remember that little trick, pressing X twice. Pressing X once gives you the overview. I could now select my own box, but I just use the box that's there already, X, and then I get this profile view. I zoom in by holding down the control button and make the points a little bigger. And now I can see my ground classification. I can press G and U. G, U. Ground, unclassified. So, looks pretty okay. I press A, I look at all of them. Now I walk around a bit and look at other areas. Why is a very different looking area with lots of ground vegetation. G, U. G, U. All. So it looks like, and this is how it looks, you see. Under the trees, the laser didn't reach everywhere. Yeah? So if I wanted to hide from the laser, I would go where the really dense vegetation is and go close to, something up here. We can also look at the returns. Which are returns actually on the ground, colored by return. And you see, of course, the last returns are the ones on the ground, but not. Here's also last return, and here's the last return. A subset, a small subset of the last returns. I press G now. The ground points are composed of single returns and last returns, last of many. This is a single return. Single return is also a last return, where the laser directly sees the ground. And here next to the trees, it's mostly last of many returns. Okay, so I do have a ground. So congratulations, you did your first LiDAR processing. We turned an unclassified point cloud into a ground classified point cloud. And now we can use this to generate a derivative, a LiDAR derivative. We will now generate a raster that you can then load into any GIS package. So, last to them, and it says at the top, it will raster the LiDAR by constructing a temporary tin into all kind of different grids.
So the white color area where the signal has not gone, I want to get what is that area possible.
But there's nothing there.
That is very useful for biomass or the canopy density.
Oh yeah, there's a tool called LAScanopy,
Okay.
which can compute in different layers how much LiDAR is there. Like how many points are between 1 meter and 3 meters compared to all the points. And then you can see, almost nothing reached here, despite the vegetation being 11 meters high. Okay, there's a tool called LAScanopy, which is used for all kind of biometric computation. I'm not covering this tool today, but I can point you to the website, which goes step by step, including the data, how to do it. So, first, when I make a raster, I must decide on the raster cell size. Now, usually, I first need to know what's the resolution of my LiDAR, how dense when the pulse is fired. I didn't do that yet because I wanted to make it a very short example. So I tell you, the pulses were fired about every 33 to 36 centimeters from each other on average. That means, I think the best I can hope for is a 40 centimeter raster. So I put 0.4 meters as my step size. That means in the end, every pixel corresponds to 40 centimeters by 40 centimeters on the ground. Under normal circumstances, when I really want to load it into a GIS package with elevations, I would now use this option, actual values. But actually, this particular one, I don't want to do that. This is just a little training example. I want to use the little shading. So I can look at it. So instead of looking at the real elevations, I just will shade the elevations with a light source and give me a picture of the elevations, which is for this exercise good enough. But the only difference, in actual use is this option. Well, that's not the only difference. I also need to pick. If I make a picture, I need to pick a format that is good for pictures. The PNG format is my favorite one. Because it supports transparency nicely. You can also use JPEG, but JPEG doesn't have such nice transparency handling.
Why not TIFF?
Also in Google Earth, you will see black area where there's no pixels, whereas PNG has nice transparency. For some reason,
But I don't get XYZ information in PNG.
no, you won't get it because we just now create a picture. We create a hillside shading. If you want to do real I should say Z information because they're all on a raster, so you really only get Z. Then you should use actual values and then use a TIFF. Yes. Or a bill, or an IMG, or ASCII. ASCII is an ASCII format for rasters that is not the most concise. So everything I did so far, I asked for a shading of the elevations. Remember, I also need a name. I need a name, and the name will be, I'm lazy again. Just underscore DTM. It's not really DTM, it's like a hill shaded DTM. So you could say it's hill DTM if you want to do. Because it's really a picture of a DTM, not the real DTM. But what name you give it, that's your choice. But now it will actually not produce a DTM. Not yet. And the reason is the tool loads all points and makes a TIFF, a triangulation of the points, and then makes from that triangulation, which is a surface, makes a new surface on a raster, a regular grid. But it uses all points. Well, for a DTM, I don't want to use all points. I only want to use the ground points. So now I need to do something new. I need to use a filter. I know which points are ground and which are not, but I need to tell LAStools, filter the points. Filter the points by classification. I want to only use the ground points. Keep classification, and I mentioned it once before, 2. The ground points are given, and that's just, we all agreed on that in the LAS format. Every LAS file, the ground is classification 2. Why? It's just a convention. If you want to remember, with 2 feet we stand on the ground. That's why. I think now I did everything correct. Oh, by the way, you need to not only do this and put a 2 here, you also need to press Add. So it shows up here in the list of filters. Now I have it twice, which is silly. I can delete the filter by double-clicking it. I only need it once. But I do need it. So now only the ground points will make it through into that temporary triangulation. Output, hillside shading. Oh, and where is my run button? a raster file is just a regular grid, like an image, like a JPEG, but instead of a pixel, you can have an elevation value, you can have a point density value, but right now we're actually creating a raster is just another name for image or grid. Raster, image, grid, it's all the same. I need to close this rollout directory, otherwise I don't see my run button. Ah, here it is again. And one other thing of looking at the command line is I can check if I actually do the right thing. Because this is almost like English, right? I'm running LAStools with -i, that means the input file is the one with the _g. I keep classification 2, I keep the ground points. With a step size of 0.4 meters, 40 centimeters, I create a little shading, and I give the file the appendix till DTM, and I output it in PNG format. It's like English without articles and adjectives, really. And now I press start. It now triangulates all the ground points, all the points that pass the filter, and rasterizes it. Now please don't stop this tool. We use it again now. And now we do some command line editing because it's very fast. I'm running it one more time, but I'm only using the pop-up box this time. So be a bit careful now. I run one more time. And now I also want to compute the surface model, the DSM. So first I need to change the name so I don't overwrite my previous result. DSM. But of course, just changing the name won't do anything. It will still create a DTM. Just name it wrongly DSM. In order to create a DSM, I also need to filter differently. Instead of keeping the ground points, I need to keep the first point. So I need to, and now you must be very careful that you don't mess up the command line. I delete the 2, and maybe I put some extra space. Extra spaces are okay as long as they're between commands. And I write here keep first. And this is now one word. There's nothing, no parameter, no 2, nothing. Just keep first. That is a new filter that keeps only the first return from every laser shot. And that's typically, when you have an airborne survey, the ones very up high. Except for when there's a bird, then it's the wrong one. So if you have a lot of birds, you need to first remove the birds before you create a DSM. So this is actually command line use of LAStools already. It's assisted a little bit because we just modified a previous command line. But that's how I do it. If I do LiDAR processing, I take the command lines I've used in the past, which I store in the text file, and I open one of them and I look to the one that's closest to what I want to do next time. I'm not starting from scratch every time. So it's actually a lot less typing than you think when you do command line. The menu buttons in all their settings I cannot easily save. But the string I can very easily save. And it also tells me in half a year, what exactly did I do? You can just look at this. Ah, that's what I did. So I press start one more time, and now I make a second run, computing something slightly different. Computing a DSM, again hill shape. Okay, now we can inspect the results, and I think we should be just done before lunch. So I go to the Poland folder, and I should have my results there. Because remember, I just changed. I don't know if your computers, if anybody's online to some secret network. I'm not online because my secret network, which usually works, doesn't work in this room. But we do have the two PNGs. One is in DSM. And if I double click on that, I see, I don't know which image viewer you have installed, but this is my image viewer here. I see the DSM. Now the DSM has a hill shape. It is a digital surface model. And as you would expect, I can see all the trees that we see before in the point cloud. But we also created a DTM, right? So for me, I just have to, no, the other one. A hill-shaded DTM, and here it is. And now I can go back and forth between the two, and you notice how the laser penetrates into the forest like it was not there. Almost. I mean, look at this road here. This road here is very well defined here and here. It is not so well defined here, and it's a bit washed out here. Why is that? Well, because that's where the vegetation is. You don't see any road in an orthophoto, and you don't see any road in a DSM. It is only the laser being able to peek through the vegetation that you can still see the road. Yes, it's not as well defined as here, but it's clearly defined. I know exactly where the road is. Also, I can't see it at all in an auto image. Notice that nothing changes in the open areas. In the open areas, maybe here a little bit because there's some low vegetation, but also here in the open areas, nothing changes. Only where I have vegetation or anything else, here is very low vegetation. I'm removing completely the vegetation and I can see the bare terrain. Now you may ask yourself, why are there bumps in the ground? Any idea? I don't really see the bumps here. And you see nothing in the orthophoto. If you have Google Earth, you can just double click the KML file. It will go to the place in Google Earth. But I'm not online right now, but that's okay. You will see it's densely vegetated here. Well, not as dense as tropical forest. This is plantation forest. It's some kind of pine, so it's fairly easy for the laser to go through. Your forests, I mean your native forests, are much harder. But you wonder, what is this? Did they plant fish ponds in the middle of the forest? That was my first guess. No, actually my first guess is my software must have made a mistake. But no, it definitely looks like man-made construction because, or maybe it's not man. Maybe it's aliens? No, it isn't man. We are in Poland here. Turns out, anybody any idea what it is? Anybody knows European history? What happened in Poland? A lot. About 70 years ago? Yeah, Poland got a lot of the brunt because they were the first country that Germany walked into, and when they had to walk back, a lot of fighting happened in Poland. So what you see here is actually Russian tank or Russian artillery diggings. They dug in very briefly. Whenever they hit some Germans, when the Germans were retreating, you know about that, right? I mean, there was a time when when some Germans, and a lot of Germans didn't say too much or were applauding, where we also, like in some other countries right now in the world, we had demagogue, who was very seductive to the gullible people. You tell them a lot of stories about how powerful and blah 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 Germany needs to be again. You know, he basically wanted to make Germany great again, much greater, and he walked all over the place. And eventually the plan, like those big plans often do, unrolled. And that was when the plan unrolled in 1944. The Russian tanks were marching forward on Hitler Germany. And whenever they encountered resistance, they dug in. I didn't know that, but afterwards somebody told me, and made these temporary fortifications just by digging a hole in the ground, really. And then waited for supply and just started shelling until it was quiet. And then they continued to march forward. And that is one of those typical lines of heavy artillery or tanks. And you can see they are all pointing sort of this way. Each one has, if you look carefully, has a little dot next to it, where sort of the people that operated it were. And you have a second line in front that's probably like heavy machine guns or something to protect the position. And I looked at the larger picture, and if you look at the bigger picture, like a half a kilometer this direction, you see German trench lines and lots of bomb craters all over the trench lines. That was a total surprise for me, because I had just given a lecture to forestry students in Poland, and I randomly picked a tile from their forest. So, oh, let's try this one. What's that? I've never seen something like this before. But there's quite a few of these lines. You know, you see one battalion, another one up there. There's a few more if you look at a larger area. So that was, it's basically a form of archaeology called conflict archaeology. And I met a German who was going around, and he was looking for old bunkers. He was almost retired. He was like 60 years old, and he told me, I asked him, why are you so fascinated with old German bunkers? He said, well, my dad used to build bunkers during the war times. So when I grew up, I actually lived somewhere near bunkers. But my dad, you know, he didn't like to talk much about the past. And when I wanted to go out play with my buddies, my dad would always say, but don't go to play by the bunkers. Bunkers are bad. Now, if you tell that a child regularly, this guy's totally obsessed with bunkers now, because you know, your dad said, don't do that. You definitely will do that, right? So now he's just, he goes with his GPS, bunker hunting, and marks it down in a map. And he had a big problem finding some bunkers in a very dense forested area in Poland. And I told him, well, we got all this LiDAR data. Why don't you come have a look? So I had LiDAR data, and he had approximate locations for where he thinks the bunkers are based on old maps and so on. And then we just crossed, and we saw we had a common intersection. So I did the hill shading just like that, and you can see that on my blog. And you can see the bunkers under the vegetation. And then, because I was there the weekend, I said, you know, why don't I come with you? I'm curious now too how that looks on the ground and how well we could see it. So we went there, and indeed, we pretty much found all the bunkers under the vegetation. And it's very peaceful now there. It's mushroom, you see lots of people going mushroom hunting, everything is green. You can see all the pictures on my blog if you just type in the search box German bunkers or something. And he got really interested by it. So he wanted more LiDAR. You know, I mean, he is not an IT person. His job is something completely different. But he then asked me, how can I get more LiDAR for other areas in Poland? I said, I don't know, but the government, you know, has a lot of LiDAR. I know the European Union paid a lot for the LiDAR, so technically we're European Union, you know. We should be able to get it since we helped paying for it. And so he wrote some letters and so on. It took about 9 months, And he had to pay almost 1,000 euros in fees, but he got 1,000 square kilometers of LiDAR, including all the NATO troop exercise facilities. So much about security again. And then he was able to teach himself how to do LiDAR processing, not because he needs to do LiDAR processing for any particular purpose, but only because there is data, and he has a particular passion, so he taught himself, with a little bit of help of mine, how to process LiDAR. And it's not entirely open LiDAR in Poland yet, but at least it's accessible. I think a lot of people in Asia, and I'm not just talking about India, I'm talking about Singapore, I'm talking about Thailand, I'm talking about other countries, even in Germany, we would be happy to pay for only an administrative fee, like I think it was €1 per square kilometer for the secretary to fill out the forms, to document it somewhere, and finally send you a hard drive full of data. But then people are able to do stuff, new things, like making archaeological maps of where the old bunker positions are, for example. And he just does it for himself. He collects bunkers like other people collect stamps. No, he doesn't publish it, just for himself. All right, I think now it's time for lunch, and when we come back, this was just a little teaser. We do a real full-blown LiDAR processing pipeline. All right.